Hi, welcome back. This is Mr. Powell, and I am going through 24 through 33. Sorry about that. I'm going to go through 24 through 33 here to try to finish this review for quarter three. On these problems, remember that the universal set are all the possible numbers that we're choosing from. Now for 24, we don't even need to know that. We have A union B, which basically means A or B. So what we are doing here is we're going to look at set A and we're going to look at set B, and as long as we see it in one of those sets, then we're going to include it in our solution. So the set here is going to be 1 because we see it in at least one of it's actually in both, but we do see it. Then we do see the number 2. There is no number 3, but then we have the number 4, the number 5, the number 6, the number 7, and the number 8. So actually, all we need to do is see the value for it to qualify for the union or in set A or B. 25 is definitely a little bit more complicated. I'm going to start on the tail end here just so we can talk about the complement. Basically, 3, 4, 6, and 7, those are the values that made it to set C. So the complement of C is basically talking about the values that did not make it to set C from the universal set. So remember, the universal set is 1 through 10. 3, 4, 6, and 7 made it. So 1, 2, 3 did make it, 4 did make it, 5, 6, 7 did make it, so 8, 9, and 10. Those right there are the values that are actually the complement of C. So that's what the complement of C is right there. So now this one, we're going to intersect that in a second with what we get from here. Well, first of all, we have to do A or B. Now I'm going to not be lazy, but hopefully be wise here and know that I just found A or B in the last problem. So A or B is right there, but what I want to use now is the complement of that set. So out of all of the values 1 through 10, the numbers 1 through 10, these are the ones that were in A or B. I now want the complement of that. So 1 and 2 made it. 3 would be part of the complement. 4, 5, 6, 7, 8 all made the set, but 9 and 10 would be the complement of that set. So now I'm going to take that set and intersect it with here. So to color code this a little bit for you, finding the complement of that was here, and now we're going to take the intersection of those two sets. Well, that means, are there any values in common amongst those sets? So I have a 3, here's the 9, 9 is in both sets, and 10 is actually in both sets, but the 3 is not. So the actual final answer to this problem would be 9 and 10. Okay? Now moving to number 26. We have 8 names on a ballot. We're going to select a committee of 4 people to serve in this committee. How many different committees are possible? These committee problems, when there's no role assigned, those are combination problems. So it's a combination of, I have 8 to choose from and I'm choosing 4. Of course, you can use your formula for that. We've taught you how to do that, but at this point, you can absolutely use the calculator, and you can see that there are going to be 70 different committees possible. So committees without roles assigned, that's going to be a combination. Now number 27, different question. You got to notice this. From 10 names on a ballot, we have a president, vice president, and treasurer. It is definitely different to be the president than to be the vice president. All right, if you pick 3 kids, you can actually come up with different possible situations. One kid could be president, one could be vice, treasurer, and you can move those all around. So what we're getting at here is that is a permutation because the order at which you select them is important. So permutation of 10 that we are choosing from, and the roles we're choosing are 3 roles. So permutation of 10, choose 3 in that situation for this permutation is actually equal to 720. Alright, now how many arrangements are possible in a true-false test? Right away we're going to notice that we're allowed to have repetition. This is not asking about the questions, it's actually asking about the arrangements of answers. So since repetition is okay, we're not going to think permutation or combination, but we would set it up as the first question has two possibilities, true, false. The second one, two possibilities. Third one, two possibilities. And we would do this, the fourth question, fifth, sixth, seventh, and eighth, and we would realize this is the exact same thing as 2 to the 8th power. So that's actually going to come out to 256 different arrangements of answers with just 8 questions, and the answers being true, false. Now number 29, a theater offers a choice of 8 movies, 4 sizes of popcorn, 3 sizes of drinks, and 6 types of candy. How many possible movie, popcorn, drink, candy deals are there? Now, reading this and from what we've done in class, basically understand that we're going to pick one of each for these scenarios. Probably should have been a little bit more specific with that, but we have 8 choices of movies, then we have 4 sizes of popcorn, 3 sizes of drinks, and then 6 types of candy. So we just multiply those together. And after doing so, we're going to see that there are 576 different possibilities there. All right, and now this one should be, very straightforward that we're going to use that special formula because we have this unique situation where we have repetition of letters. If there was no repetition of letters, the answer to this problem would be 11 factorial. But the problem is you can see right there 3 P's, so some of these scenarios will repeat. So instead of just having 11 factorial for our answer, we're going to use that as the numerator in our special formula, where technically every time we see a letter, we put that letter however many times we see it, factorial. Well, we only see a C once, so there's no point in writing 1 factorial since it's just 1. So the main thing we're going to do here is we're going to look for any of this repetition so that we can put those in our formula. So C doesn't repeat, O doesn't repeat, but P does repeat 3 times. Okay, so that means we're going to have 11 factorial over 3 factorial, and then E repeats. Okay, so we can see that. I'll just try to circle. There's an E here and an E there, so that's going to give us 2 factorial. And investigating here, we don't have any more repeating going on, so we're going to go ahead and work on our formula, try to get the answer. If you look over here, we do have a factorial button, so if I hit 11 and the factorial button is right down here, it pops up as something that's not seeming to work right now. Let me try to make this a little bit bigger and see if that helps. Okay, I don't know how it's coming up on your screen, but I cannot see that real well right now. So what I'm going to do is I'm going to try to find it a different way. And I think it's just not showing up well on my screen. So luckily, I know what 11 factorial means. I know that that means 11, and that's going to be times 10. Times 9, times 8, times 7, times 6, times 5, times 4, times 3, times 2, times 1. Now I didn't need to do all of that there, but just kind of showing you that all of that is what 11 factorial is equal to. Okay, so for ease here, I'm going to hit enter so we can see what that number is, but then we're going to take that number and we are going to divide by, and I'm going to put this in parentheses, 3 times 2 times 1 times 2 factorial, which is 2 times 1. And then when I hit enter, I will get my answer here of 3,326,400. Alright, so I am actually going to have that many letter arrangements just from the word copperplate. Move this back over a little bit here. Alright, so we only have a few more questions here. Number 31. We're going to roll 2 fair 6-sided dice. what is the probability that the sum of the numbers on dice will be 6 or 2? There's different ways to think about this problem. I like to list out just all the possibilities. So first of all, we just think about summing to 6. First one could be a 1. Second one could be a 5. There's a sum of 6. We could have a 2 and a 4. We could have a 3 and a 3. First one could be a 4, second one a 2. And then we could have a 5 and a 1. But we can't have a 6 and a 0, 0, 6. So we have the sum of the dice being 6 or 2. So there's one other scenario that's a success here, and that's if you have the 1, 1, what we like to call snake eyes. So looking at all the successes, if you simply add up all the successes, you see that there's 1, 2, 3, 4, 5, 6. There's 6 successes. And like all these die problems we've been talking about, there's 36 possibilities. 6 choices for the first die, 6 choices for the second die, for a grand total of 36 different possibilities. 36 different scenarios. So we have our 36 as our denominator. So when we reduce that, we get 1 over 6. Now another way to think about it is to really think about this or in the way we've been teaching or as an and. So if you do that, you think about these being the successes for the 6. So you just think about it as 5 successes out of 36 possibilities. And then the or really being the and sign. So then the or is the addition. And then we have, well, only one situation where the sum of the die would be 2. So that would be plus 1 over 36, which you can see we're still getting to 6 over 36. Still the exact same answer of 1 over 6. Okay, so 2 ways to think about that. And we can basically do that throughout the rest of the probability problems. These are hard for number 32, some people to put in their heads and what's going on. So I would suggest possibly making a little chart if it helps you out. You have juniors and you have seniors. And then in this problem they are talking about males and females. So maybe a little chart might help you. There are 10 juniors. Okay, so out of this column here we're going to have 10. Of the 10 juniors, 4 are male. So there are 4 male juniors and there are then 6 female juniors. 12 seniors total, 7 male. So the 7 male seniors are here and a 5 goes right there. So they're going to ask us what is the probability that we could have somebody saying yes to I'm a junior or I'm a female. Well, first of all, it's important to note that the number of students are the number of possibilities here, so the denominator is 22. All right, so I'm going to highlight here what we think a success would be. Well, a junior. Okay, these juniors here are successes. You know, for part A here, junior is definitely a success, or a female. So these people would also be raising their hands. So if we just counted all of them, we would say 4 plus 6 is 10, plus the 5. We're going to have 15 out of 22 that are saying they're a junior or a female. Okay, and then let me make sure I did that right. Sorry. Okay, and then the next scenario would be I'm a senior or I'm a male. Well, if I get my highlighter here, senior or a male. And the phone is ringing at my house. So we will be patient here.
Hello?
Okay, sorry. Minor delay. Carry on. So a senior or a male. So the seniors here in red, senior is a success. Right here. The seniors will definitely be raising their hands. 7 and 5. And then a male is also a success. Okay, so these 4 are raising their hand. All of these are raising their hand. So I have 11 plus 5. I have 16, which will be the successes here. So 16 out of 22. All right, so that's going to reduce in this one to 8 over 11. All right, going on to number 33. A spinner has regions of, let's see, 1 through 30. What is the probability the spinner will stop on an odd number or a multiple of 3. Well, we got to understand the main important part is there could be some overlap here. So odd numbers, if we were to list out all of the odd numbers, and we're going to do this for illustrative purposes here, so bear with me. I have a purpose in here. 21, 23, I think I'm going to run out of space, 25, 27, and I got it in there, 29. All right, so there are all of the odd numbers. So 1 through 30, there's all the odd numbers. Those are all successes in here. Well, we have that many right now. If we want to do it this way, we could say, okay, well, out of there, that's 15. You know, that's half of the numbers would be successes. But we have another thing that's a success, a multiple of 3. So if we listed out the multiples of 3, starting with 1, although, okay, so that would be 3, 6, 9, 12, 15, 18, 21, 24, 27, and then 30. Well, if you just add all of these together, these are, every number that you see on this paper now is a success for this scenario. But the problem is we can't just add them all up and divide by 30. Problem is that we've overlapped some of them. If we take our highlighter here and we look at the ones that have repeated, okay, so I've got 3 here and here, 6 did not, but 9 did, looking through 12, 15 did, 18 did not, 21 did repeat, 27 repeated as well. So the question is, how many successes do we actually have? Now each teacher will teach this differently, but I like to just think of, well, let's look at all those odds. All of the odds up there, that's 15. I have 15 successes up there. And then just count all the successes down here on the bottom that were not already counted in the top. So in that scenario, I'm not going to count anything in yellow here on the bottom again because I already accounted for it at the top. So I've got 15 along the top. I count every single odd number up top. And then what more am I going to add? I'm going to add 6, 12, 18, 24, and 30 to that. So I have 15, 16, 17, 18, 19, 20. I have 20 successes. So our probability is going to be 2/3 for that problem. Okay. Now switching gears, and I will switch to a different color so you can see that this is a different way of thinking. You could definitely think of this problem as 15 successes out of 30 for it to be an odd. And then we could add to that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We could add to that 10 successes out of 30 because there's 10 places where it's divisible by 3. Problem was there was overlap, so we could subtract the overlap, which is 1, 2, 3, 4, 5. There are 5 situations of overlap. So if we go through this, you will see that we have 15 plus 10, 25 minus 5, which gets me to 20 over 30. Again, reduces to 2/3. I hope you have enjoyed this review, and I hope you put in the time to do well on our quarter 3 tests.